From the very beginning of human history, new ideas have been inspired by the potent combination of curiosity and observation. In today's technological world, everything you touch, use, see, or do, from striking a match to sailing, railing, emailing, flying, cutting, drying, tying, threading, sledding, trucking, chucking, plucking, timing, climbing, rhyming, typing, swiping, hyping, wiping, tracking, cracking, jacking, texting, requesting, talking, walking, chalking, or watching this show is possible because someone, somewhere, observed, experimented, and transformed what was once just an idea into a useful and powerful tool. As incredible as these innovations and inventions are, they may soon pale next to what these explorers, past and present, have discovered and are uncovering. By peering into and probing the depths of the most powerful and weird universe imaginable. The quantum universe, a paradoxical realm of seemingly unlimited potential, where fascinating phenomena are being harnessed and developed into new technologies that may alter the world as you know it. Journey into this weird and progressively wired world with the Quantum Tamers. Humanity's first inkling of the quantum universe begins in 1900 with one Max Planck, a brilliant physicist who was trying to figure out why objects changed color as they got hotter. But wait a minute, we're getting ahead of ourselves. Before we get to quantum physics, we need to know a little about classical physics. First, there was this famous guy named Newton, who with a few simple mathematical equations described and predicted the motion of the planets. This was a powerful idea.
Isaac Newton understood the power of mathematics. He understood that not only we can encapsulate a bunch of facts or data into a simple equation, but that we could use this simple equation to predict the future. What he discovered is that the world is fundamentally predictable.
Next, a gentleman named James Clerk Maxwell showed that electricity and magnetism could also be summarized with just a few mathematical equations.
Maxwell's equations had a tremendous impact on the technological development of last century, the 20th century, to everything we see around us, TV, mobile phones, and many of these very useful technological tools that we use. All are outcomes of this tremendous revolution that Maxwell initiated.
Now, between Newton and Maxwell, scientists thought they knew how the real world worked. Things orbited around each other, and pretty much everything that was transmitted, including light, came in waves, like the ones you see when drops strike water. We'll call these brilliant observations the classical world, a world where everything is predictable and looks familiar. Which brings us back to Max Planck, who launched us into the quantum age, the age of lasers, CDs, computers, and personal communication devices. He was studying something that was far removed from these futuristic devices. As I said earlier, he was trying to figure out the mystery of why objects changed color as they got hotter. Now you might wonder why anyone would want to study something that's so, well, so...
We might say that this is a boring question, but for physicists it was very interesting.
And if Max Planck hadn't found this seemingly boring subject fascinating, we might not have quantum physics.
Just as Isaac Newton had used the laws of classical physics to describe the familiar world around him, Planck also wanted to use this approach to understand why objects changed color as they got hotter. But what he found was that the laws of classical physics weren't working. They gave the wrong answer. So he tried a whole new approach, a whole new mathematical hypothesis. And when he did that, it worked. He got the right answer. But the problem was, this new hypothesis didn't fit with the laws of classical physics.
Planck had provided an extremely accurate explanation, but he did not believe it himself. The first person to take Planck's idea serious was a young patent clerk at the Swiss Patent Office, Albert Einstein, whom nobody knew at that moment.
Einstein figured out something that Max Planck couldn't believe that light is not just a continuous wave. Sometimes it behaves like a particle. Physicists call this wave-particle duality.
One of the greatest intellectual achievements of Albert Einstein, the one he got a Nobel Prize for, was to realize that light acts as if it came in pieces, in chunks, quanta. Quanta of light are called photons. The inkling of that came before in the work of Max Planck, but in his work it was just a mathematical artifice. Einstein realized it's just not mathematics, it's really physics. And he drew consequences and explained experiments which could not be explained with waves.
Einstein's work marked a major turning point in the development of modern physics. Then in 1913, Niels Bohr started filling in the quantum picture by explaining the structure of the atom using these simple equations. Okay, maybe not so simple if you don't speak math.
Bohr was able to explain the properties of atom using quantum mechanics. He used a model called the planetary model, which is similar to the Earth going around the Sun, where, in the case of atom, it is the electron going around the nucleus.
But Bohr's math showed him that electrons didn't orbit the nucleus of an atom in quite the same way that planets orbit the sun. Instead, they could orbit the nucleus only at certain specific distances, something quantum physicists call discrete distances, or quantization.
And this was deeply unsettling to a generation of physicists who had been brought up on the notion that things change smoothly. For example, the way the moon circles the Earth and the Earth circles the sun.
But Bohr's postulation assumed that electrons behave like particles. It took French physicist Louis de Broglie to show that atomic orbits can be explained by assuming that electrons, normally thought of as particles, can also behave like waves. But each of these postulations on their own didn't provide the entire picture, and the quantum conundrum had disconnected dots that went from Planck to Einstein to Bohr and then to de Broglie. What was needed was a theory to connect those dots and clarify how a wave could act like a particle and a particle could act like a wave, to explain the mystery of the wave-particle duality of light and matter. And in 1925, Erwin Schrödinger formulated the now famous equation that bears his name.
Schrödinger's equation really laid the foundation for what became a full theory of quantum mechanics. And this new theory not only gave scientists a universal recipe for understanding all of the previous quantum phenomena, but it also gave scientists a systematic way to explore the atomic world to find new quantum effects, unexpected ones. Ultimately, the quantum theory gave scientists what is probably the most accurate and most powerful theory ever devised by humanity.
While the discovery of quantum theory was enormously useful as a scientific tool and made many of our modern-day technologies possible, it actually raised more questions than it answered. Many of these questions are illustrated by the famous double-slit experiment, an experiment that, to this day, sets physicists' hearts aflutter.
The double-slit experiment is actually a metaphor for saying wave-particle duality. What does it mean? In classical physics, we have waves, like sound waves or electromagnetic waves. And we have also particles like billiard balls. After quantum mechanics, a particle, like an electron, can also sometimes behave like a wave.
The double-slit experiment is so exciting to physicists and so interesting to everyone interested in quantum mechanics because it contains the essence of quantum mechanics.
In the double-slit experiment, a beam of electrons strikes a battle with two narrow parallel slits in it, and then a screen.
When we do this experiment with the lights on, nothing unusual happens. The electrons form the same pattern on the screen that you would expect for spitballs or wads of gum or even tomatoes. But when we turn the lights off, something very surprising happens.
What one observes on the screen is a series of maxima and minima.
This series of maxima and minima is known as an interference pattern.
Maxima are places where electrons accumulate. Minima are places that they avoid. The interference pattern is what you'd expect to see if you sent waves, not particles, through the double slit.
What we observe in the double slit experiment is explained mathematically by Schrödinger's wave equation, which predicts exactly the observed interference pattern. But quantum theory doesn't tell us where the particle is as it goes through the slits.
The essential difference between classical and quantum physics is that in classical physics one can predict both the positions and the velocities of particles, whereas in quantum theory one can't predict either.
Why is the pattern on the screen different, depending on whether the lights are on or off?
In classical physics, we are used to the universe which is independent of us knowing about it or not. We can look at it, but whatever it does doesn't change. It doesn't care. It runs according to its own rules. This is no longer the case in quantum mechanics. They're looking at something, making an observation of it, changes how it behaves.
But how can this be that in the quantum world, by just observing something, you can affect the way that it behaves? In our everyday experience, observation just means looking. It's a very passive thing to do. But remember, observation always requires light. And in the quantum world, light comes in chunks, called photons. To see this, let's turn the theater lights back on and see exactly what scientists mean when they use the words observation and measurement. So in order to observe how the electrons pass through the two slits, you have to shine light on them. But when you do this, the photons can cause the electrons to behave differently. In this case, the photons make the electrons behave like particles. And so the interference pattern at the screen goes away. So now that we see what's happening when the lights are on, the question is, what's really going on when the lights are off? On this question, scientists have diverging opinions and some mind-bending speculation.
The double slit experiment shows that as long as the quantum object is not being measured or interacting too strongly with its environment, it typically doesn't have a definite position. It's typically spread out over many positions. This is what we call quantum superposition.
Quantum objects behave as if they can be and they can do several things at the same time. Electron can go through two different slits at the same time. This reminds me of Yogi Berra, who said, when I get to a fork in a road, I take it.
These radical ideas showed just how much quantum superpositions challenge the classical notion of reality. But these ideas troubled many scientists, including Erwin Schrödinger, who realized that if superpositions could be amplified to the everyday world, they would lead to bizarre predictions. To illustrate this point, he conceived a Gedanken experiment.
A Gedanken experiment is a thought experiment. That is, an imagined scenario that helps us to focus on some conceptual issue. If you really understand a theory, you should be able to say what the theory predicts in all sorts of situations, including some that can't be carried out in an actual laboratory.
Schrödinger's famous thought experiment has come to be known as Schrödinger's cat.
Schrödinger's cat is kind of a parable about the idea of quantum superposition.
Schrödinger was disturbed by the implications of quantum theory.
Apparent paradoxes in quantum mechanics.
He wanted to show how absurd quantum mechanics is.
He came up with Gedanken experiment.
The thought experiment.
This was the idea. You take a cat. A cat's a cat.
An unfortunate cat.
And you put it in a box.
Completely isolated from everything on the outside.
In this box as well is a hammer and a beaker
Filled with cyanide.
And there's also a control mechanism in the box, which is controlled by a single atom, which can radioactively decay.
Now, when the atom decays,
The detector activates the hammer.
the vial will be broken
The cyanide will be released.
And that is going to kill the cat.
and the cat will die.
And if it doesn't emit the particle, the poison is not released and the cat is alive.
Now suppose that after, say, an hour, there's a 50% probability that the Geiger counter will have detected something.
Until we look inside, the possibility exists that the cat is either alive or dead.
And if we believe quantum mechanics, then the cat at that point is in a state which is simultaneously dead and alive.
Schrödinger's point was that it's absurd to think that the cat is somehow simultaneously dead and alive just because it's described by a superposition. And so similarly, we should reconsider how we think about electrons in superposition.
One answer you could give is to refuse to answer the question. You could say, well, quantum theory is just a set of rules for making calculations to tell you where you're going to detect light, and that's all. This is a so-called shut up and calculate school. All these different sorts of answers have been given by different physicists. There's no general agreement, and it'll probably be a long time before there is.
Now, while physicists can disagree about whether to take this idea of the cat being simultaneously alive and dead seriously, the important point is that superposition cannot be explained away in terms of familiar classical concepts. And this is exactly what makes quantum mechanics so intriguing.
Like Schrödinger, Einstein continued to be puzzled by this apparent paradox.
Einstein felt that everything could be understood if only a deeper theory could be discovered, one which was more complete. To make his point, he came up with a new Gedanken experiment with his colleagues Boris Podolsky and Nathan Rosen at Princeton. They showed that certain combinations or superpositions of particles could combine in a bizarre and counterintuitive way that could not be explained by classical mechanics. The result is what's called the Einstein-Podolsky-Rosen or EPR paradox.
The thesis itself was somewhat difficult for the layperson, and perhaps even for scientists, to understand.
Ready? Okay. In a complete theory,
an element corresponding to each element of reality.
A sufficient condition for the reality of a physical quantity
is the possibility of predicting it with certainty without disturbing the system.
Then either one, the description of reality given by the wave function in the quantum mechanics is not complete,
or two, these two quantities cannot have simultaneous reality.
One is thus led to conclude that the description of reality as given by a wave function
is not complete.
So what does this fairly dense statement mean? According to quantum mechanics, it's possible for two particles to be so tightly intertwined that they form a single system in which neither particle has a quantum state of its own. What Einstein, Podolsky, and Rosen said is, okay, let's take a pair of particles like that and separate them very far, maybe light years apart. Then imagine an observer over here measuring particle A, and thereby giving it a state which it did not have before. The key point is that when that measurement is made, it also determines the state of particle B, a state which, according to standard quantum mechanics, did not exist previously. For Einstein, this was impossible. How could a measurement over here affect something instantaneously that's light years away? So he and his collaborators concluded that the state of particle B must have existed previously, and therefore that quantum mechanics was incomplete. The idea of making a measurement over here and having it change something over there is what Einstein would have called spooky action at a distance.
Einstein believed that the world should be ultimately knowable, that there should be a reality out there. And quantum mechanics defied that. It didn't work this way. Einstein did not like that. That sparked his comment, God does not play dice with the universe.
Many early quantum physicists, including Einstein, hoped that a deeper theory would be free of the apparent contradictions of quantum mechanics. Some scientists hoped that the weird quantum elements were just going to go away.
After Einstein had introduced in 1935 the concept of what he called spooky action at a distance, it was the Austrian physicist Erwin Schrödinger who named this phenomenon in German Verschränkung and in English entanglement. The point is that Verschränkung is a better way to call this. Verschränkung is something like this, a very strong, well-defined connection, while entanglement sounds a little like spaghetti, not very well-defined.
Suppose we think of two entangled particles as a pair of dancers. If the dancers can't see or talk to each other while they're dancing, it is possible, though difficult, for them to remain in sync. They can do it only if they've pre-rehearsed which dance moves to follow and so on. Einstein hoped that the properties of entangled particles could be described in the same way, that the correlated way in which the two photons react to any possible measurement could could be explained by having the measurement results predetermined. But Einstein was wrong. We now know that entanglement is a connection between particles that's stronger than any that can be shared using classical physics.
These quantum curiosities, of which entanglement was the oddest, puzzled researchers for over a quarter of a century. In 1964, Irish physicist John Bell designed an experiment to actually test what Einstein thought was impossible.
The Einstein-Rosen paper of 1935 was basically ignored for the first 30 years of its existence. Then John Bell came and showed that a basic, simple explanation of entanglement is not possible. This gave rise to fundamental experiments where people wanted to know, is nature really that crazy? Is nature really that strange?
John Bell's paper on entanglement coincided with the development of the laser, which made these experiments possible.
When I read the paper by John Bell, I discovered what entanglement was. And this was absolutely fascinating. Reading that paper was a shock, something like love at first sight. You know, this paper was explaining us that the big debate between Einstein and Bohr about the foundation of quantum mechanics could be settled by doing an experiment. I was an experimentalist. I wanted to participate to settling that debate. The basis of the experiment is to produce pairs of photons which are going to fly in opposite direction. And then, when they are separated by 12 meters, to make measurement exactly at the same instant. And the idea is that the two measurements, separated by 12 meters, must be separated in the sense of relativity. What do I mean? I mean that what I measure on one side should not be able to influence the result of the measurement on the other side. This is a critical point. Special relativity tells us that nothing can travel faster than light. So it means that what I do here has no time to flow to the other end of the experiment. And for that, it was necessary that I could change the orientation of my polarizers in a few nanoseconds. Achieving this was a crucial and new part in my experiment. And what I did was to measure the polarization of each photon. Photons can be vertically or horizontally polarized, or polarized at 45 degrees. Now, a pair of EPR entangled photons is simultaneously vertically polarized and horizontally polarized. This is pretty strange. As strange as the Schrödinger cat, which is alive and dead. And now the question is, what is the result of the measurements? And in this strange situation, I found what was predicted by quantum mechanics, which is that whatever direction of measurement on one side, if I choose to measure along the same direction on the other side, I discover that both photons look aligned along the same direction. This means that the results of the measurements are strongly correlated, more correlated than any conceivable correlation in classical physics, in the classical world. It means that when the two photons are separated by 12 meters, they still behave as a single whole object. Einstein thought this was not possible, because it would mean that there is a kind of spooky action at a distance between the two objects. But if we want to reconcile the result of the experiment with an image we want to build, we have to put the spooky action at a distance in our picture.
Einstein never really understood the fundamental difference between classical and quantum theory. That is why he found it so difficult to accept things like the uncertainty principle. But quantum theory agrees with observation. God really does play dice with the universe.
Before John Bell and later Alain Aspect came along, all we could ever really do was just argue about the weirdness of quantum mechanics. The Schrödinger equation tells us that a cat can be both alive and dead, and nobody knows what that means. It's just weird. And these arguments went on for decades. What John Bell did was put some mathematics and some quantities around the quantum weirdness, and what Alain Aspect did was come along and verify those measurements in the laboratory. So in essence, between John Bell and Alain Aspect, we were able to measure the weirdness of quantum mechanics.
Alain Aspect's experiments established that these quantum effects were real, even if it wasn't clear how to make sense of them, using our normal way of thinking. What's more remarkable is that these experiments inspired a generation of scientists to ask, how can these weird quantum features be useful?
Quantum mechanics gives us a phenomenally accurate description of the behavior of light and matter. This understanding helped 20th century scientists and engineers develop all sorts of technologies, including, for example, the laser and the transistor, which are at the core of our electronic world. These relatively large-scale quantum devices function without, in any overt way, exhibiting the weird aspects of quantum mechanics that we've been talking about.
These familiar technologies are all products of the first quantum revolution. But now a second quantum revolution has arrived, based on two major developments. First is the technological ability to directly control the weirdness of the quantum world, including superposition and entanglement. And the second is the rise of the information age. So ready or not, here comes quantum information, or QI if you're texting.
Well, what got me thinking about quantum information was in 1985 I came across a paper by the American physicist Richard Feynman in which he talked about the possibility of computers operating on quantum principles. And this came like a bolt from the blue for me, because up until that point I was more accustomed to thinking of information in very abstract terms. In the ordinary everyday world, it's difficult for us to separate the idea of information from content and meaning. But we can get an idea of why information is physical if we think about, for example, what we would do if we were asked to point to information. And we would always point to a piece of paper with marks upon it. We might point to an optical fiber. We might point to a hard disk. In the case of a hard disk, we can see that information really does have some physical content. For example, when you want to store some information on a hard disk, you have to pay real money. You have to go out and buy, say, a 100-gigabyte disk. It doesn't matter what the information actually is, but the fact that there's a certain physical quantity there that you pay real money for tells you that in reality information is physical. For example, I'm talking to you now. Information is being conveyed using sound. I could write a letter, and the information would be stored as ink and marks on paper. Once you get the idea that information is physical, you then begin to wonder whether the laws of physics either constrain how information can be processed, or, in the case of quantum physics, gives you a completely new mechanism for processing and communicating information.
This is information. The proper use of it can bring a new dignity to mankind.
Now you're wondering, classical information, quantum information, there's a difference? There is, and it all starts with the humble bit.
A bit is a fundamental unit of information, of classical information. It is encapsulated into physical system which can have two states, either something which is on or off, something which is charged or discharged, or something which is here or there, or, in mathematical terms, a 0 or a 1. In the quantum world, we have quantum bits, or for short, qubits. And these qubits can be in superposition of being in 0 and 1 at the same time.
And it's the ability to manipulate the world at that level of quantum weirdness, of quantum superpositions, that enables us to do computational tasks in quantum mechanics that are impossible, or at least very difficult, using conventional computers.
Our technologies are already approaching the boundaries of quantum information, and our transistors are approaching the size of a quantum bit or a qubit. And we have called this Moore's Law in honor of the founder of Intel, who predicted it 20 years ago. And in fact, over the course of the next 20 years, we expect the transistors, which are the heart of our computing devices, to approach the size of a single atom.
So the second quantum revolution really consists in us today being able to manipulate individual quantum systems, individual molecules, individual atoms, or in my case, individual photons, where so far after the first quantum revolution, we were able to manipulate ensembles. For instance, a laser would produce billions of photons, not individual photons, but billions. And today, the fact that we can really manipulate, master individual quanta, as we call them, opens a huge new area for technological developments.
One of the first accomplishments of this second quantum revolution is the ability for physicists to build incredibly precise tools, like an atomic clock, the world's most accurate timing device.
These days, the precision of atomic clocks is such that we're able to if we made a clock and if we could keep it running for about 60 million years, it wouldn't lose more than 1 second. It turns out the added bonus of the precision and quantum control we're able to achieve with the atoms we use for atomic clocks also is the basis for good qubits.
So if you can control individual qubits, you have an amazing clock. But if you can scale up and control the interactions of dozens or hundreds of qubits all at the same time, you don't just have a bigger quantum clock. You create a quantum computer, which has the potential to be the most important invention of our time.
Quantum computation can be considered a revolution in the theory of computer science. What we think today is that quantum computers will be able to perform certain tasks exponentially faster than classical computers. And why is that? So there is this very important fundamental thesis in computer science called the modern Church-Turing thesis. And what it says is that all regular classical computers are essentially equivalent. It's not that they exactly perform with the same speed, but they act according to the same rules, they behave similarly, and if you tried to perform some task with, say, your laptop, and then you try to do the same thing with another computer, it will sort of behave approximately in the same way. Quantum computation, it just is completely out there, out of this equivalent class.
Quantum computers are based on the fact that the quantum state of a computer memory contains much more information than its classical description.
The quantum computer will also be different in that it will manipulate and store quantum bits instead of classical bits. Classical bits can be in 2 states, 0, 1. Quantum bits can be in many possible states. And this new range of possibilities lead to new phenomena such as entanglement and interference. And we believe that this is what can give a quantum computer its power, these new phenomena.
Just how much more powerful? And to what end?
Well, one of the first applications of a quantum computer, and one of the most useful, is to simulate quantum systems. This is not something that most people are probably going to want to do at home, but it still has huge potential applications.
So to understand quantum simulation, it's important to think why we just need simulation at all. So consider an aircraft simulator. Why do we have an aircraft simulator? Okay, an aircraft simulator is a box. You go in, it's got a wheel, it's got a joystick, it's got instruments, and you go in there in the box, goes back and forth, you move up and down, you take your simulated 747 in for a landing, like that. Why do we have that? Well, we don't want people taking real 747s in for a landing until they know what the heck they're doing, okay? So quantum simulation is the same thing. You have some big, complicated molecule. It's like a 747 of molecules, right? This gigantic thing, it's exhibiting all sorts of weird quantum behavior. You want to know what to do with it, but you don't know how to control it. You don't know how to make it do what you'd like it to do. So what you do is you simulate it on a quantum computer.
For instance, a quantum computer might help design new superconductors to run magnetic levitation trains, or new drugs to treat diseases. And a quantum computer could help simulate the atoms in the drug to tell us both how to make the drugs and how we'll interact with other chemicals.
Others foresee a different role for quantum technologies.
Quantum mechanics is now giving us the tools to sense things better than we've ever sensed them before. We can sense mercury in fish. We can sense lead in toys. We could perhaps sense bombs along the side of the road. Using quantum mechanics, we can make the sensors more robust, more precise, more sensitive, and we can compact the sensor. We'll be able to use these sensors broadly in an environmental setting.
But what caused an explosion of interest in quantum computing was Peter Shor's discovery.
Well, what I did was I showed that if you could build a quantum computer, which is a hypothetical computer that no one has managed to build yet, you could use it to factor large numbers. So if you take 2 numbers, say 3 and 5, and multiply them together, you'll get the number 15. Now, factoring is the reverse of that process. You start with the number 15, and you want to take it apart say that it's 3 times 5. So for 15, it's pretty easy. You can do it in your head. But suppose you took two 200-digit numbers. Well, with enough patience and paper and pencil, you could multiply them together to get a 400-digit number. And computers can do that in a snap. But if I gave you the 400-digit number and told you, find the two 200-digit numbers that were multiplied to get it, I don't think you can do it. And in fact, even the world's most powerful computers, that is a problem which is essentially impossible for them to solve. The factoring problem is used to encode most of the important secret messages that are sent today. The way it works is that, say, when you buy something over the internet, your computer multiplies two 200-digit numbers together to get the 400-digit number. And now, anyone can encode things if they know the 400-digit number, but to decode it, you need to know the two 200-digit numbers. And nobody can figure those out from the 400-digit number because the factoring problem is almost impossible to solve.
Shor's discovery was so exciting because what Shor says, essentially, is give me a quantum computer and I'll be able to crack the most common and most important way to encode secrets.
Governments take the development of a quantum computer very seriously. As a threat, a quantum computer can break many of the encryption codes that are in use today, including those codes used on satellites, those used by banks and credit cards for secure communications.
But just as theoretical physicists saw that a quantum computer could crack secret messages, they also realized that quantum effects could be used to create the world's ultimate secret codes, quantum codes, providing a super secret way to keep information private.
In classical cryptography, we usually make the assumption that the system is secure because the eavesdropper, the would-be eavesdropper, can't solve some difficult computational problem. Quantum cryptography works on a different principle. You can't break a quantum cryptographic code unless you can break the laws of physics.
With quantum cryptography, it's essentially impossible to eavesdrop on the transmission without being detected. We might call this the noisy observer effect. It's as if you were at a party and were listening in on a neighboring couple's conversation. They know instantly, without even looking, that they're being overheard.
Quantum cryptography is already being used at a high level, securing election results in Switzerland.
So in this lab, we developed the basic technology for quantum cryptography. What was secured by quantum cryptography is the fiber optic link that connects the place where the paper ballots are counted to the place where the state's computer are located. And that was the first public real-world applications of quantum information.
Quantum cryptography is just one of the many powerful quantum tools being developed and deployed at the moment. But the most fantastical and mind-bending application is a phenomenon known as quantum teleportation.
Quantum teleportation will not be anything like what you see in science fiction. The reason is that no matter is transmitted from point A to point B. It's the quantum information that gets transmitted from point A to point B.
Quantum teleportation is made possible by entanglement. One uses the entanglement of two photons to transmit the information from one over to the other one. In 2004, we did a quantum teleportation experiment across the river Danube. We ran a glass fiber cable from one bank to the other over a distance of 600 meters. This fiber ran through a sewer, and therefore we call it the third man experiment, remembering the movie The Third Man, which was staged in the sewers of Vienna, starring Orson Welles. This is the only movie where the theme is played by a zither. We create these entangled photons by shining a strong laser into a special crystal. And then a photon of higher energy can decay into two photons of lower energy, which are then entangled. We send one of the photons over to the other side of the river and keep the first one locally. This photon then meets a third one, the one to be teleported. By entangling these two, the quantum properties of the third one are transferred over to to the particle on the other side of the river, and teleportation is finished.
So quantum teleportation is one of the most beautiful demonstration of entanglement. So in quantum teleportation, we really have that something, quantum state or the ultimate structure of matter, disappears on one side and reappears on the other side without ever existing in between.
But the 2004 experiment is Schnee von gestern, which means yesterday's snow. In the long run, we want to go up to satellites, that way establishing quantum communication on a worldwide scale.
We now know the power of quantum information, but what will it take to realize the full potential of this technology? What will it take to build a quantum computer?
The principles of quantum computing are well understood. It is only their implementation in practice that is difficult.
There is no problem in principle with building quantum computer. That's very clear. We know how to put together strings of quantum operations on paper and how they will end up giving us a quantum computer. The problem is in translating it into real hardware.
A quantum computer requires maintaining quantum superpositions to perform correctly.
Just like in the double slit experiment, where the superposition and the resulting interference pattern on the screen were lost if the electron is observed or measured in any way. Similarly, the quantum computer derives its special power from maintaining large-scale superpositions of all of the qubits. This means keeping the quantum computer very well isolated from its surroundings and protected from any unwanted interactions until the computation is complete.
Superposition states are very hard to preserve.
In Dr. Wineland's lab, the qubits are stored in what is called an ion trap.
The analogy to our ion trap and a marble in the bowl is the following. We can think of the marble being the atom and the bowl being this so-called trap, the way we hold the atoms. And one thing we can do, for example, with our atoms and the marble in the bowl here is we can put the marble in a circular orbit going around the center of the bowl. And we can do this with our atoms as well. Now, with the marble in the bowl, we usually, at some instant of time, you realize that the atom, say, is going to be on the left side of the bowl or the right side of the bowl. Now, the strange thing in quantum systems, which allows us to make qubits, is that we can put the atom in a superposition state in its bowl, its trap, so that it's, at some instant of time, it's not on the left side of the bowl or the right side of the bowl. Rather, it's both on the left side of the bowl and the right side of the bowl at the same time. So the analogy with Schrodinger's cat is that we're able to make situations where we have a superposition of all the atoms pointing in one direction and all the atoms pointing in the opposite direction at the same time.
So what might a quantum computer look like?
Behind me you see a prototype for a quantum computer. It's made of a very powerful magnet, which is made of superconducting material, which is bad at liquid helium at about minus 266 degrees Celsius. The qubit in that system are made of the small magnet inside of the nucleus of atoms. At the end of a computation, we're using the magnetic field of these qubits to be able to read off the answer of the computation. This particular quantum computer has a dozen of quantum bits, or the equivalent of 1,000 classical bits, which is computers of the 1950s. If we're able to build a quantum computer with about 60 or 70 quantum bits, then we'll be able to have a quantum computer which is more powerful than all classical computers combined on Earth.
Today, scientists are pushing the limits of theory and experiment from blackboard to lab, harnessing the power of nature's mysterious quantum world, laying the foundation for a new era of discovery and innovation.
Quantum theory, quantum theory.
Quantum Tamers.
The potential is huge.
System Tamers.
This is Quantum Tamer.